So I'm just gonna put this somewhere here. Okay, so I'm just gonna create another file here to have the correct implementation. So I'm just gonna copy that. And paste it. And then let me call this something else. So let's say that call this increment. Okay. So we don't want this counter to be dependent on the execution context of the function. So we will take it out and put this add function as an inner function in another one. So let's say the outer function will be called increment. Okay, and the variable will be out there. And then the inner function would still is still fine. Don't need to change anything because it does have access to the counter through the closure scope, right? And then I will just return that function. So I want to return the function object. Okay. So now I will call the inner function. So let's say I'm just gonna call this add step. Now I don't need to change the name because it is from it. The name is in the local scope, but just to make it obvious that we had to call the outer function, we need to call this increment function and receive what returns in order to have access to the entire closure. Okay. So now you see this execution lines are the same, right? But now we're not just executing the inner function per se, we're executing it inside the closure that came after we called the outer function. Okay, so let's trace it and see what happens inside. All right, so now we are about to execute the outer function. All right, so I'm just gonna step inside. Now we have something called the add step that doesn't have anything, it's undefined right now, right? And then we would have the counter also, so now initialize to 0. And then see what happens here with the undefined once we execute the definition step of the function. Now the function object is created, right? Now the closure scope is accessible through the object of the function, regardless whether it is executed or not, right? Now there is no execution at all at this moment. We didn't try to execute this inner function at all, right? So the closure, the access to the closure is independent of the execution of the function. All right, so the closure scope right now has access to a variable called counter, which is equal to 0. Okay, now let's see, we are about to return from this function. And what returned was received in the variable called add from outside, right? Now see, we didn't try to execute add yet. And we ended the execution of increment as well. You see, this doesn't exist here in the call stack. If we just examined the function object itself, now part of the function object is the code, the definition of like the code itself that would be executed when you call it. But in addition to that, regardless whether it's getting executed or not, it still have access to the scopes. And one of these scopes is the closure scope. And at this moment, the counter is equal to 0. We didn't execute anything yet. Now we are about to have the first execution for this closure. Okay, the function that came out with its surrounding context. Now I'm gonna step inside to execute the code. Now we see now we have a context, right? That context still have access to the closure that has a counter at the moment is equal to 0. We're going to update that. Now it's equal to 1. And we are about to return from the function for this execution. And once we return its context, we're about to return right now. Once we return, its context is discarded. The context of the execution is discarded. But the closure scope is still accessible because it's accessible from the function itself. So where is the function? Here. So we ended the first execution and its context was discarded, right? But the closure was not discarded. Still have a variable called counter, but now it's equal to 1. Right? So that's still now in the last session, we've seen how the variables accessible through the closure are read. Like we were able to access them to read. But we can also update the values too. And they will remain inside the closure scope and independent from the execution context. Now I'm gonna try to execute that function again. Let's step inside. Okay. So now this counter that was accessible through the closure now is equal to 2 because we just incremented it. All right. And this is the context. This is the frame that is in the call stack that represents that execution context. Once we return, what happens? Once we return, the execution is discarded, but the closure is not discarded. And it is accessible through the object of the function. And right now, it has a variable, the counter variable has a value 2. Okay. Now again, I will execute it again. And now the counter of the closure is now equal 3. So every time we execute the function, it creates a new context, but the closure is independent of the execution context. All right. So now when we print that, it works as we want. Okay. Now let's take it one step further to compare between the variables which are read and variables that are updated. So I'm just gonna copy that. Paste. So let's say we want to increment with a step. Okay, so at the moment we increment by 1 every time. Okay, what if we want to have a step? So I'm just gonna use another variable, here in the outer context. Okay, and to add 1, I will have to send the value I want to be added as an argument. Oh, sorry. To the outer context here, outer function. Okay. So now I want to send a step, and every time we want to increment, we increment with that step, not just 1. So when we say increment by 1, it should have the same effect as we had before, but let's see it. Now we see this, the closure of this add function has two variables now. One is called step, and that's currently equal to 1, and the counter that's equal to 0. So last time when we learned about the factor, we just had one of the variables in the closure fixed, okay, and created a closure, the concept of that based on that fixed value. But it doesn't have to be fixed, which is just the way we wanted to use it is that in the multiplier is to have the closure always multiplied by 2, right? That we wanted it to be fixed, so we didn't attempt to change it. But we can change it if we want it, like we did with counter here. Okay, so here I created a closure that adds 1 every time. Okay, so if we keep adding, now counter is equal to 1. Now counter is equal to 2. And when we print 1, 2, 3. Okay, now I can repeat that and create another closure that adds 2. So increment by 2. So I'm just gonna remove the definitions and we'll use the same variables. All right. Now if I print these, so the add has a closure with a step equal 1. Okay, so every time we add 1 to the counter. Step outside. Okay. Now here we are creating a new closure. So you see add 2 is still undefined here, but once we call increment with an argument 2, we are creating a new closure. So the same function definition, but it's coming from with a new closure, a different closure that has a step equal 2. So when we run that, we will see that the add 2 is now pointing to a function object. If we open it, we will see that it has access to a very similar closure, but the value of step here is equal to 2. All right, now when we step and we execute the function, every time would add 2 to the count. Okay, so the point is that the variable in the closure doesn't have to be fixed. We are able to change it as well. Okay, now what if we want to have an increment by 3? Or a closure that adds 3 every time? We just need to call this function outer function again with an argument equal 3. Okay? All right. Any questions? All right.